Welcome back again. This time we're going to look at series parallel circuit calculations. So up to this point we've looked at simple series circuits and we've looked at simple parallel circuits, and now we are going to combine those two concepts together into series parallel circuits. The first thing we're going to look at is current flow. That's almost always the first thing we look for. So in this we have part of our circuit which has total current, and that's the part that you see going up with the red lines. And then of course we have another part of our circuit, which is the parallel part of our circuit, where we see current divided, and those are those green lines. In this particular circuit we have two branches, but you can have as many as the circuit requires, and the calculations and the logic behind it are all the same. Alright, so once we have looked at where current is flowing, the second thing we're going to do is look at total resistance. Now when you start to calculate total resistance, you're going to start out in your parallel, and you're going to first combine your parallel branches, the components within your parallel branches and the branches themselves, into what we call a resistive equivalent. Now this has resistive equivalent as REQ. It's not unusual to see that as RE. And you'll see that resistive equivalent is calculated just the same as if you were doing total resistance in a pure parallel. You're going to reciprocate the ohmic values of your branches. Now in this case, all of our branches have only one component, and so we have our calculation with just R2 and R3. And we find that our total resistive equivalent, or the resistance on our parallel, is 1K ohms, or 1,000 ohms. As we've discussed before, this can be also expressed using the R over N method. Now the R over N method is pretty simple. It's just kind of a little shortcut way to get to a total value without having to necessarily put it into your calculator. And what you do is you take the number of branches that have the same resistive value, and you take that resistive value divided by that number. So in this case, I have two branches that both have 2,000 ohms in them. So I can take 2,000 divided by 2, as you can see in this formula, 2,000 divided by 2, and I end up with a total resistive value of 1K ohms, which is exactly the same as if I had reciprocated it like I did on the first example. So we're going to take that part away just for a little bit. I just wanted to throw it up there so you can see that you can do your calculations this way in parallel if you do have multiple branches that are the same, but we're going to try to reduce some of the confusion here with all the numbers that are going to go up for the circuit and take that away for now. Alright. So once we have the resistive equivalent of our parallel, we're going to start looking at total resistance. And it is quite simple to get total resistance. All you do is sum your resistive equivalent with your series connected resistors. Now in this case, we have only one, which is R1. And so we will take our resistive equivalent, which was 1,000 ohms, and add it to the resistance of R1, which is 2,000 ohms. And we get a total of 3,000 ohms. So we have total resistance. The next step is going to be total current. So we use Ohm's law. We're going to take voltage divided by total resistance. So in this case, that would be 12 divided by 3,000 ohms, and we get a total current of 4 milliamps. So now that we have the resistive equivalent of our parallel, we have our total resistance, and we have our total current, we can start looking at voltage drops. And we're going to go ahead and start with the voltage drop of our series resistor, or R1. So it should be no surprise by now that we are going to take the resistance of R1 and multiply it by total current. So 2K multiplied by 4 milli gives us 8 volts. Now, if you think about it, if I'm going to drop the entirety of my voltage in my circuit and R1 has 8 volts, if I take 12 minus 8, I know that my parallel must have 4 volts. However, you can also use the calculations to figure this out. Sometimes there are multiple series resistors, Sometimes it's not quite as simple as this particular circuit, and so it's nice to be able to just do one quick calculation to find out your parallel voltage. In that case, I would do the same way I did it for my series resistor. I would take the resistive equivalent of my parallel and multiply it by total current. So I would take my 1K ohms and multiply it by 4 milliamps, and I get a total voltage of 4 volts. I know, not surprising. So 4 plus 8 equals 12. Our math looks to be perfect. So now we're going to look at branch current. First we look at branch 1, and it's no surprise that just like in parallel circuits, we take the voltage applied to the branch and divide it by the resistance in the branch. In this case, EREQ, or the resistive equivalent of the parallel, is the voltage that we are going to use. And we're going to divide that by 2,000 ohms, which is the resistive value of branch 1. And we get a total current of 2 milliamps. Now we're going to do the same for branch 2. And no surprise, since we've got exactly the same ohmic value, we get exactly the same current. Now we know that current is divided in parallel, so it's not much of a surprise that I have 2 milliamps and they add up to 4 milliamps because that is total current. So where these red lines are right here, I have 4 milliamps, and then where these green lines are, because I have the same ohmic value in each branch, I also have the same current in each branch. So total current of 4 milliamps split in half. Half of it went through branch 1 and the other half of it went through branch 2. And then up here on the top side, it meets up again and we have 4 milliamps again all the way back over to the positive side of our voltage supply. Alright, so one last thing we're going to look at. We're just going to take a quick look at the voltages and how they all add up. So first off, you'll notice that voltage is constant in parallel, like we have always learned. So the voltage of branch 1 and branch 2 is equal to the voltage for my resistive equivalent, which is 4 volts. And if we combine the parallel voltage and our series voltage, we end up with applied voltage, or 12 volts. Alright, so that is the end of series parallel circuits. I hope you learned something, and next we are going to cover opens in a series parallel circuit.